Okay, so last time we did that activity with the dice and we were looking at the sum of our dice rolls. And here I have the data from our whole class. So from everybody, okay, all your dice rolls compiled together. Here was our frequency table and then our histogram, right? And I asked you guys to find all of these pieces for our data. I, together with you right now, want to talk about the shape of this data because that's going to lead us into the problems that we're going to talk about today, okay? So this should be similar to the histogram that you have on your own paper. I want you to notice it's shaped like a mountain, right? Like a big hill. The highest part of the mountain is in about the middle of our values, right? We went from 2 to 12 as our options, so about the middle is where the highest point of our data is, where my tallest bars are. And then as I get away from that, my bars start to drop down, right? The height of my bars is shorter, okay? Our shortest bar was 12, but our second shortest bar was 2. And sort of as I work towards the middle of my data, the bars get taller, right? And in the middle, again, is where I have that tallest bar. This is what we call, or what we see when we talk about a normal distribution or a bell curve. And that's what you saw in your notes last time, right? So if I flip ahead a couple of pages, one page, I guess, this is what you looked at last time, that bell-shaped curve, and we looked at how that data was spread, okay? So what we're gonna do today is work on some practice problems that go along with this. So I'm gonna hop to page 24. That dice activity was our introduction to this idea of normal distribution, this idea of this bell curve that we can see. So for the next couple of days, everything that we're going to work on is going to be normally distributed or roughly normally distributed. That curve we saw for our dice, if I flip back for just a second, is not a perfect normal distribution, but we could say it's roughly normally distributed. And as I talked about in the notes video, there's a lot of things that we'll see in real life that are, if not perfectly normally distributed, then roughly normally distributed. Height is one of those things that I talked about, and you saw some examples about that's roughly normally distributed. Number of siblings tend to be normally distributed. Most people have, we'll say, an average of 3 siblings and are pretty close to that 3 number. So there's a lot of things that we see in real life when we talk about maybe like specs on like different animals or plants or things like that. All of that is roughly normally distributed, okay, which is why we care about this particular distribution. So on page 24, we're going to work through some example problems. Let's scoot this up here a little bit. And let's start with number 1. Number 1 says Farmer Brown has planted a field of experimental corn. By judicious sampling, it is estimated that there are about 20,000 plants and that a graph of their heights looks like the one shown below. So plant height, that's another, it's a height again, right? The time of plants instead of people, but that's again something that I would expect to be normally distributed. When I drive past a field in the summer, most of the plants, if they're corn, if they're beans, if they're whatever, most of them are about the same height, right? I might get a couple that are really tall or a couple that are really short, but most of them are about the same height because that's normal distribution. That's how things grow. So I've got a graph here of my corn. I want to know, what is the mean height of the corn? So remember, our mean is always under the center, right? The highest point of our curve, that's our mean. So our mean for this corn is 100, and our label is inches. It says our height is in inches. So the mean height of our corn is 100 inches. What's the standard deviation? So here's our mean, and then our standard deviation is how much I add or subtract as I move away from the mean. So our next line is labeled as 110. Our mean is 100. One line up is 110. That means our standard deviation is 10 inches. With me so far? Okay. Part C, what percent of the corn stalks are between 90 and 110 inches tall? So from 90 to 110, that's one standard deviation on either side of the mean. That graph, that curve that we labeled at the start of our notes had those percentages in there. These are each 34%, okay? So 34% here, 34% here. I'm just gonna add them up. And I get 68% So I would expect 68% of my stalks for my corn to be between 90 and 110 inches tall. Okay. Over 2/3 of them, I would expect to be within one standard deviation of the mean. And then for part B, about how many stalks are between 80 and 90 inches tall. So 80 and 90, that would be from here to here. And again, since we're looking between two standard deviation lines, I'm just going to use that percent that we labeled in our notes. This would be 13.5. So 13.5% of those stalks. Now it says how many, not what percent. So I have to go back to my problem directions intro here at the top, and it says I had 20,000 plants. So I'm going to find 13.5% of 20,000. And we would get 2,700 stalks there. Questions for me so far? Okay, so far we've really just relied on those percentages that we labeled on that first page of our notes. Let's hop down to number 2. This time we're going to draw the curve. So for number 1, we had it given to us. For number 2, we're going to sketch the curve ourselves. Number 2 says, suppose you were informed that the annual income of lawyers is normally distributed with a mean of 40,000 and a standard deviation of 10,000. Draw a normal curve to represent this. So I'm going to draw the base of my curve first. It looks something like this. Okay. Mine are never going to be perfect. I don't expect yours to be either, as long as it has that bell shape, okay? And we put the mean under the middle. So our mean goes under the middle, and it says our mean is 40,000. So I'm going to put a 40 there. And then again, 3 chunks on either side. 1, 2, and then 3 at the very end. Same thing over here. 1, 2, 3 at the end. And then we label these with our standard deviations. So our standard deviation is 10. That means as I move forward on my curve, I'm adding 10 each time. So this would be 50, 60, 70. As I move backward on my curve, I'm subtracting 10 each time. So this would be 30, 20, 10. And these are all in thousands. So there's my curve. Okay. What would you estimate for the percent of lawyers with incomes over $50,000? So over $50,000, let me do some color coding here so we can take a look at what we're seeing here. Over 50,000 would be 50,000 or greater. So those are my top 2 pieces of that curve, 50,000 or greater, okay? So that would be, I could take these 2 pieces and add them up, or I could use the fact that my curve is symmetric and say, take the top half of the curve, subtract off the piece I don't want, subtract off the 34%. You're going to get the same thing either way. I'm just showing you a different approach if you'd like. Okay, so you could also say 13.5 or 13.5 plus 0.25, and you're also going to get 16. 2 approaches you can take there. Add these 2 chunks, or take half, subtract the part we don't want. So percent of lawyers, could have also done this just with our percentages, since it says percent, 16%. What percent of lawyers would you estimate have an annual income of less than $20,000? Less than $20,000 is just this bottom chunk here. Okay. So that would be 2.5%. Just that bottom section. Part D, if a lawyer were selected at random, what's the probability that his or her annual income were more than $60,000? More than the 60 would be just our top chunk here, more than 60. So that's again, 2.5%. This time it asks for probability, so I'll leave it as a decimal, since that's how we did probability with our tables earlier in the unit. But again, I'm just looking at that bar chunk between 2 and 3 standard deviations. That's 2.5% no matter which side of the curve I'm looking at. And then finally, E, if the information given here were correct, would you think it very likely that 50% of all lawyers have annual incomes over $50,000? Why or why not? So they're saying 50%, half of all lawyers have incomes over $50,000. Does that match what we're seeing here? No, right? 50,000 is up here. That's more than, or that's 1 standard deviation or more from the mean. If they said 40,000, I would buy half of all lawyers have an income of 40,000 or more, but not 50. Okay, so I'm going to say that would not be likely, since $50,000 is 1 standard deviation above the mean. And that's what we found with part B, right? We said that's about 16%, not half. Questions for me so far? Okay, let's turn the page and let's look at a few more practice problems. On page 25, we're starting with number 3 at the top. We've got 2 different curves here, distribution A and distribution B, and we're going to pick out some information for each of these. Notice we've got a lot of notation here, okay? We want to practice using that. This curly Q guy, remember that's standard deviation. The O with the little like cowlick happening there, that's standard deviation. That's what that means. And this kind of goofy looking U, that's mean, okay? So I want to know the standard deviation of A and B. What am I going to look at to determine the standard deviation on these curves? How are these different, right? The difference between any 2 labeled values on my curve. And it doesn't have to be between the center one and the next one over because it's the same across the whole curve. So for A, what's our standard deviation? 10. And then how about B? What's our standard deviation here? 5. What's the mean of A? 40. Yeah, it's going to be that value in the center under the highest part of the curve. How about B? 65. Very good. In A, what value corresponds to, we're seeing the term Z-score here. You guys are going to see that in your next round of notes. So we actually will skip these and come back to them. But the idea is we're going to look at moving off the mean by whole standard deviation increments. So we'll come back to B and C in our next sort of set of practice problems. Let's hop down to example 4. So for example 4, examine the normal distribution below and determine what % of scores you would expect to be between, for A, 40 and 50. What % of scores do you expect in here? 34%. Since it says what %, I'm just going to leave these as percents. For B, between 20 and 50. So here and here. How did you get that?
I looked at the other page and between
yeah, so you look back at the chord problem and said, I know what the distributions were for this one. So between 30 and 40 would be 68, right? Because this is 34 and this is 34, but we get one extra chunk here. So what do I add on for the extra chunk? 13.5 of that other percent, right? I just add all those pieces up, the same ones that we worked on for the corn example on the last page. So 13.5 plus 34 plus 34 would give me 81.5%. And then for C, between 10 and 70. So between here and here. Well, that's our whole curve, right? That's everything. So well, how much would I expect? What percent would I expect to be in there? About 100%, yeah. I'm going to say about 100% because there is a possibility that I could have what we would call, again, those outlier values, points that do fall outside of those 3 standard deviations. That's possible. And so I'll say about 100 to allow for that possibility, but it would be very odd to have something more than 3 standard deviations per minute. Questions for me on 4? Okay, now let's take a look at number 5. Okay. Number 5, grades on a history test are normally distributed with a mean of 76 and a standard deviation of 4. There are 60 students who took the test. I want to know approximately how many students had scores within these given ranges. Okay, so this again is going to be kind of similar to that last part of the corn problem. I knew how many stalks we had, so we wanted to know how many stalks do I expect to be about this height. So we're doing the same thing here. It doesn't ask me to sketch a curve for this one. I'm going to anyway, because I am a visual person, so I like to have the visual there. It says my mean is 76 and my standard deviation is 4. I also like to have the sort of numbers that I'm working with labeled on a curve, so that's why I draw out the curve. And again, standard deviation of 4, so add 4, 80, 84, 88, subtract 4, that would be 72, 68, 64. So for part A, I want to know how many students had grades within 1 standard deviation of the mean. So this means 1 standard deviation below to 1 standard deviation above. This middle section right here, okay? So we know this part's 34%, we know this part's 34%. I'm going to add those up. And I know it would be 68% of my kids. Now it says how many, and we know that there were 60 students who took the test. So I'm going to find 68% of 60. This would give me 40.8. Since we're talking about people here, I'm going to just chop off that decimal and go with 40. That we didn't get all the way to a 41st person. So I'll say here approximately 40 students. For part B, had scores greater than 80. Greater than 80. So 80 or bigger would be those top 2 sections. So from 80 to 84 would be 13.5. And from 84 to 88 would be 2.5. We looked at a section of a different example where we looked at these 2 pieces. And so we shouldn't be surprised at 16%. That's what we found earlier. Now I'm going to find 16% of my 60 students. So 60 times 0.16 gives me 9.6. So I'll say about 9 students. And then for part C, had scores less than 80. Scores less than 80. So 80 or below. Just to save myself a little work, I'm going to take advantage of the fact that this curve is symmetric and cut in half. And so instead of adding all of these pieces up, instead of adding these 3 things, I know that that's half the curve. So I'm going to use 0.5 for that part, 50%. We'll do percent. This part's 50%, right? And then this part's 34. So 50 plus 34 gives me 84%. So I'm going to find 84% of 60. That gives me 50.4. So approximately 50 students. All we did for each of these was use those same percentages from that very first curve, okay? 34 on either side, 12 and a half, or 13 and a half, 2.5, okay? 34, 13 and a half, 2.5 on either side. Our curve is symmetric, so that makes it easy. Questions for me for today? Okay.